33 trillion kilograms. That staggering weight is the minimum astronomers now assign to the newest wanderer from beyond our solar frontier, the interstellar body known as 3-1 Atlas. To grasp its immensity, imagine the Empire State Building multiplied not by hundreds or thousands, but by 40,000. Yet even that comparison barely captures the scale. This immense traveler drifts silently through the void, releasing plumes of gas that jet outward, but astonishingly, its orbit shows almost no sign of recoil. It is like beholding a freight locomotive driven forward by the flicker of birthday candles. And still, the mystery deepens. With an object of this magnitude, logic dictates we should have encountered countless smaller cousins first. We did not. The implication is stark. Either our map of cosmic rubble is profoundly incomplete, or 3-I Atlas embodies a truth about interstellar matter that unsettles everything we thought we knew. Part 1. The Shockwave Announcement. New analysis suggests that 3-I Atlas weighs no less than 33 billion tons, with a nucleus stretching 5 kilometers across or more, several orders of magnitude above anything we have previously glimpsed drifting between the stars. If these estimates hold, our view of interstellar debris has been violently redrawn. The figures were not conjured from speculation but from the meticulous work of the Harvard Center for Astrophysics, where researchers processed 4,022 positional measurements supplied by 227 observatories scattered across the globe. This is no longer conjecture. It remains a lower limit and still preliminary. Yet the implications loom immense. Let us momentarily step away from the equations. Astronomers detected almost no measurable non-gravitational recoil, the tiny rocket push that normally betrays a comet's gas jets. In this case, the ceiling sits beneath 15 meters per day squared, which translates to roughly 2 times 10 to the negative 9th meters per second squared. When translated into everyday units, those values describe forces so delicate they blur into the noise of the instruments themselves. And yet the puzzle sharpens. Faint push combined with visible activity demands tremendous mass, colossal mass. The rocket effect is straightforward physics. As a comet warms, frozen ices vaporize into gas. That gas escapes, producing narrow jets that act like miniature thrusters, nudging the nucleus on its journey. We have seen this spectacle countless times before. Yet 3-I Atlas complicates the script. It displays fountains of activity, water vapor, carbon dioxide, even more exotic volatiles, yet the expected nudge is conspicuously absent. The simplest explanation is dauntingly direct. This object is massive beyond expectation. Why does such heft matter? Recall that Oumuamua displayed a mysterious acceleration that unsettled astronomers for years. By contrast, 2Y Borisov behaved like a standard small comet, a comforting reminder of the familiar. But 3-I Atlas brings something unprecedented, a heavyweight acting like a comet, yet dismissing its own exhaust as if a mountain were unmoved by morning mist. For the first time, we confront a category of interstellar visitor that does not fit our previous boxes. The scientific community's reaction has been riveting. Researchers voice curiosity laced with skepticism. News reports accurately echo the emerging narrative about enormous mass, but everyone underscores that these findings remain unreviewed. Extraordinary claims must submit to ordinary process. That balance of excitement and restraint defines good science, but the tension is almost tangible, as though the field itself is holding its breath. What do we know with certainty? This is only the third confirmed interstellar object ever discovered. The Atlas survey first spotted it on the 1st of July, 2025, from their Chilean observatory. The Minor Planet Center officially christened it C 2025 N1ATLAS, though the shorthand 3I Atlas quickly took hold. 3I denotes the third interstellar object, a sobering reminder of how rare these wanderers truly are. And in case anyone worries about planetary defense, Earth is in no danger. The closest pass will occur on the 19th of December, 2025, at a distance of about 1.8 astronomical units, roughly 170 million miles. By cosmic standards, that is close, but still far enough to ensure we remain only spectators. The images deepen the enigma. On the 21st of July, the Hubble Space Telescope caught sight of 3I Atlas, revealing what astronomers described as a teardrop cocoon glowing oddly toward the Sunday. Most comet tails stream away from the solar furnace, swept back by radiation and solar wind. This object, however, exhibited an anti-tail, a glow extending sunward. That phenomenon is not without precedent, but it is rare enough to provoke raised eyebrows. By the 27th of August, Gemini South revealed the anti-solar tail had grown even sharper, its structure evolving as the body warmed. Dust, gas, and dynamics interwove into complex morphologies, each frame providing fresh clues to the mystery of mass. Here lies the heart of the astonishment. If 3I Atlas truly possesses a nucleus 5 kilometers wide and weighs more than 33 billion tons, then it is 3 to 5 orders of magnitude more massive than Oumuamua or 2I Borisov. That is not an incremental leap, but a vault from pebbles to mountains in the interstellar debris field. Statistical models had long suggested we should detect smaller fragments first. They are more numerous, easier to eject, and require less energy to accelerate into interstellar space. Yet our census began with a thin shard, then a small comet, and now a possible behemoth. It is as though we discovered the existence of mice only by stumbling upon elephants. These mass estimates hinge on assumptions, rates of gas escape, speeds of molecular flow. On the 6th of August, 2025, the James Webb Space Telescope turned its infrared spectrograph toward the object, capturing the fingerprints of what was sublimating. That data fed into models linking visible outbursts to hidden mass. But models are fragile instruments. They are only as sturdy as their inputs. Webb detected water ice, water vapor, carbon dioxide, and carbon monoxide. Remarkably, the ratio of carbon dioxide to water ranks among the highest ever recorded at this solar distance. Such chemistry points to formation far beyond the warmth of a parent star. In regions where carbon dioxide freezes alongside water, a territory astronomers call the carbon dioxide snowline. In other words, 3I Atlas carries the frozen imprint of a birthplace buried deep in the frigid outskirts of some alien system. Perspective is essential. The numbers that elevate this object to silent giant status rest on preliminary estimates of outflow, rates around 150 kilograms per second, and gas velocities approaching 440 meters per second. These values remain under revision, pending more data and peer-reviewed publication. The Webb team has not yet released their definitive analyses. Nevertheless, the physics remains stubborn. Active gas production without recoil demands explanation. Either the gas is venting inefficiently, which seems unlikely given the bright coma, or the object is so massive that it absorbs the recoil without the slightest tremor. The balance of evidence favors mass. The metaphor writes itself. Picture a freight train and imagine trying to move it by hurling tennis balls. The balls ricochet harmlessly, the train does not stir, and the onlookers suddenly understand its immensity. 3I Atlas is that freight train, an interstellar juggernaut cloaked in dust and vapor. This revelation unsettles our perception of the galactic debris field. If such hulking bodies roam the dark between stars, where are the countless smaller cousins our models predicted? Are they too faint for our instruments, eroded to nothing by cosmic radiation, or simply far rarer than theory allowed? The answers carry weight beyond academic debate. The soon-to-be commissioned Vera Rubin Observatory will survey the southern sky every few nights, potentially uncovering scores or hundreds of interstellar trespassers each year. Should 3I Atlas prove typical rather than exceptional, then our frameworks for planetary formation may require rewriting. So what evidence compelled scientists toward this silent giant hypothesis, and, just as crucial, how much confidence can we place in it? The next chapters of observation and analysis will decide. Part 2. The Silent Giant. The evidence builds into a compelling trilogy that resists dismissal. First comes the upper bound on non-gravitational acceleration, so faint that it hovers indistinguishable from zero, almost as if the universe itself is erasing the signal. Second stands the unmistakable display of cometary activity, witnessed by a network of ground-based observatories and confirmed by the eyes of orbiting telescopes, a show of vapor and dust, unmistakably alive. Third arrives the chemical fingerprint, revealed by the James Webb Space Telescope, a chemistry saturated with carbon dioxide, in concentrations seldom seen among comets at comparable solar distances. These three pillars together construct a paradox. To understand it, we must revisit the rocket effect in its simplest form. Imagine a garden sprinkler spinning in the summer sun as water jets from its arms. Each stream, though gentle, pushes back, creating rotation. Comets mirror this principle. As ice sublimates into gas, the escaping jets act as miniature thrusters that alter orbits. Astronomers have measured such non-gravitational accelerations in hundreds of solar system comets. It is considered routine physics, reliable as sunrise. Yet 3I Atlas disrupts this script. Despite vivid evidence of outgassing water vapor blasting away at hundreds of meters per second, carbon dioxide swelling into a coma stretching hundreds of thousands of kilometers, the anticipated orbital recoil is absent. The acceleration ceiling lies beneath 15 meters per day squared, essentially indistinguishable from motion driven solely by gravity. Contrast this to Oumuamua, the pioneer interstellar visitor. That strange shard exhibited measurable non-gravitational acceleration, but no visible cometary exhaust, an inversion of the problem. Hypotheses swirled. Perhaps it vented molecular hydrogen, perhaps radiation pressure acted upon an elongated geometry, perhaps something more exotic. The debate endures. Then came 2Y Borisov in the year 2019, a figure of comfort. Borisov resembled the comets we know, its nucleus roughly 1 kilometer wide, its gas emissions dominated by water and carbon monoxide, and its non-gravitational acceleration neatly aligned with predictions. It was reassuringly ordinary, proof that interstellar comets could behave like local ones. But 3I Atlas occupies a new quadrant of parameter space. It exhibits the visible breath of a comet, yet defies the physics that breath should impose. The analogy verges on absurdity. It is like watching a swimmer propel themselves without displacing water, a violation that suggests something foundational has been overlooked. The chemistry intensifies the enigma. On the 6th of August, the James Webb Space Telescope directed its near-infrared spectrograph at the object, registering not only the usual water, ice, and vapor, but also carbon dioxide and carbon monoxide in startling ratios. The carbon dioxide to water fraction ranks among the highest ever recorded for a comet at this solar distance. Such a signature implies a birthplace far from any parent star, beyond the carbon dioxide snow line, where temperatures sink below -125 degrees Celsius. In these frozen outskirts, carbon dioxide solidifies alongside water, embedding within the cometary matrix. By carrying such chemistry, 3I Atlas bears the ancient imprint of alien cold. Meanwhile, the Spherex telescope detected a vast carbon dioxide coma extending hundreds of thousands of kilometers outward, far larger than casual optical images might suggest. To the human eye through visible light, it presents as a compact, luminous heart, but infrared instruments reveal an immense, invisible shroud enfolding the nucleus. Here lies the discomfort. Even modest outflow at hundreds of meters per second should impart a detectable recoil. Conservation of momentum is not optional. Gas carries momentum, and that momentum must be balanced by a corresponding push on the parent body. For a nucleus only 1 kilometer across, even modest rates of sublimation would produce measurable accelerations, yet the data refuse to show them. More than 4,022 positional measurements from 227 observatories, collected between the 15th of May and the 23rd of September in the year 2025, map a trajectory that aligns almost perfectly with gravity alone. The logic is elegant in its simplicity. Input the gas production rate and the velocity of escape, compute the recoil, compare to observation. If reality falls beneath expectation by orders of magnitude, the object must be vastly more massive than guessed. This is celestial detective work, with the law of momentum conservation cast as chief witness. Current estimates suggest 3I Atlas is venting around 150 kilograms every second, the equivalent of 2 human bodies' worth of material, leaving the surface in each tick of the clock. Over hours and days, the accumulated momentum transfer should produce an orbital signature as clear as ink on parchment. Yet no signature appears. The absence itself becomes the message. The nucleus must be extraordinarily massive. Assuming densities typical of comets, about 500 kilograms per cubic meter, the lower bound of 33 billion tons implies a nucleus at least 5 kilometers across. This is not merely another cometary wanderer. It is a leviathan cloaked in vapor, rewriting the expectations of interstellar debris and pressing astronomers to reconsider what kinds of worlds shatter and escape into the deep galactic sea. That scale is staggering by the standards of interstellar visitors. For perspective, Oumuamua likely measured less than 1 kilometer in its longest dimension and carried perhaps only millions of tons. 2I, Borisov's nucleus spanned roughly 1 kilometer and held billions of tons of frozen material. 3I Atlas, by contrast, could outweigh both by factors ranging from 10 to 1,000, a true heavyweight in a realm once ruled by featherweights. Outflow velocity estimates near 440 meters per second arise from careful spectroscopic analysis of emission line profiles. When gas escapes a comet's nucleus, the combined influence of thermal motion and bulk flow broadens the spectral lines in distinctive patterns. Modeling those shapes yields velocity estimates, though the exercise demands assumptions about temperatures and gas dynamics. Such velocities are not extraordinary. Solar system comets regularly exhibit comparable speeds, driven by sublimation energy and the weak gravitational hold of small nuclei. What is extraordinary is the yawning gap between copious gas release and minimal orbital recoil. A simple visualization clarifies the paradox. Imagine a chart mapping comet mass against non-gravitational acceleration. Solar system comets cluster into a familiar sequence. Greater mass generally correlates with smaller acceleration for a given activity level. Oumuamua strays from the line, showing high acceleration with no visible gas. 2Y Borisov lands right on the expected trend, a faithful disciple of the physics, but 3I Atlas defies the diagram, inhabiting empty space with enormous mass paired to almost non-existent acceleration, stretching the fabric of our intuition. It behaves less like an icy body that happens to be heavy, and more like a colossal body that coincidentally releases ice. The metaphor becomes irresistible. It resembles a comet, exhales like a comet, yet shrugs off its own breath as if it were a boulder unmoved by wind. This dissonance between appearance and dynamics compels unsettling questions. Could the gas production estimates be flawed? Conceivably, but James Webb's spectroscopy anchors the outflow rates with authority. Could the acceleration data be biased? That seems improbable, given contributions from a worldwide network of observatories and rigorous error analysis. Momentum conservation cannot be suspended. Mass remains the only convincing explanation. 3. Atlas emerges as an anomalous giant cloaked in cometary disguise, its true enormity unveiled only through the precision of relentless measurement. Part 3. The Global Eye Network. The saga of 3-1 Atlas unfolds through the collective eyes of hundreds of telescopes spread across the continents of Earth. When Avi Loeb, Andrija Cloete, and Robert Verhees assembled their analysis, they drew upon more than 4,022 individual measurements contributed by 227 observatories, taken between the 15th of May and the 23rd of September in the year 2025. This campaign ranks among the most comprehensive ever undertaken for an interstellar traveler. At its core lies astrometry, the precise determination of celestial positions, the bedrock of orbital mechanics. Every telescope that turned toward 3i Atlas recorded its place in right ascension and declination, the cosmic equivalents of longitude and latitude. Each measurement, accurate to fractions of an arc-second, became part of a growing mosaic of motion traced across the star-speckled backdrop. It is cosmic detective work, each data point a snapshot, a single frame in a long exposure photograph. String enough frames together, and a story emerges. Deviations from perfect gravitational paths reveal themselves as residuals, the subtle gap between where gravity alone predicts and where the object actually appears. The precision required to establish the non-gravitational acceleration limit of 3-1 Atlas strains comprehension. Astronomers were chasing positional shifts smaller than 28 thousandths of an arc-second. To visualize this is to imagine detecting the width of a single human hair viewed from 20 kilometers away. Yet ground-based instruments, meticulously calibrated and statistically cross-checked, routinely reach such staggering exactitude. The translation from angular position to physical acceleration belongs to the realm of orbital mechanics, yet the underlying principle remains simple. Acceleration accumulates. Even the gentlest, non-gravitational force, given months of operation, compounds into measurable orbital displacement. The result of this painstaking detective story is a limit, 15 meters per day squared, which, when converted into more familiar language, equals roughly 2/1000th of a meter per second squared. That is smaller than 1/10 millionth of the acceleration felt inside a gently rising elevator. To reach such a conclusion requires weaving thousands of pinpricks of light into a single coherent trajectory. Each observatory lends its unique vantage point. Northern Hemisphere sites followed the object during summer skies, while their southern counterparts assumed the watch as Earth's spin unveiled new portions of the heavens. The timeline of discovery reads like the opening chapters of a modern astronomical thriller. On the 1st of July in the year 2025, the Atlas facility in Chile detected the visitor, initially catalogued as a possible asteroid. Recovery images, archival photographs, predating the official discovery helped refine its orbit, proving its interstellar origin. Within weeks, the Minor Planet Center had reclassified it as humanity's third confirmed interstellar object. Even the Vera Rubin Observatory, still in its commissioning phase, supplied early data that sharpened both activity profiles and orbital tracks, offering a glimpse of the survey era now dawning, when vast telescopes will sweep the southern skies every few nights, poised to uncover dozens of such visitors each year. In this sense, 3I Atlas becomes a prototype, a harbinger of the observational revolution about to unfold. Subarc, second precision grants, investigators the power to rule out non-gravitational pushes that would otherwise be unmistakable in smaller or less carefully tracked comets. At milli-arc-second scales, months of tracking allow astronomers to test the very foundations of Newtonian mechanics, transforming fuzzy points of light into exquisitely mapped journeys through the solar system. The campaign drew strength not only from world-class facilities but also from the contributions of amateurs and semi-professional networks. Their time series measurements of brightness and morphology, though less precise individually, filled temporal gaps, ensuring that as 3I Atlas brightened and evolved in its approach toward the Sun, the record remained continuous. Global coordination underscored the endeavor. Observatories handed off responsibility across time zones as night swept the planet, while radio networks choreographed pointing schedules and the Minor Planet Center gathered the torrent of observations into a single archive. From there, orbital analysts iteratively refined the trajectory, chiseling away uncertainty with each new submission. What makes this achievement remarkable is not merely the scale, but the speed. Where once astronomical discoveries might take months or years to reach confident classification, 3I Atlas progressed from first detection to detailed orbital solution in a matter of weeks, a testament to the modern age of astronomy, where global collaboration and instantaneous data sharing collapse timelines and elevate precision to heights once unimaginable. Modern computing power, automated detection algorithms, and rapid communication networks have compressed discovery timelines that once unfolded across entire seasons. The precision achieved by this global effort explains how scientists could impose such strict limits on non-gravitational acceleration. When thousands of positional measurements are gathered with milli-arc-second accuracy across months of continuous observation, even the faintest departures from pure gravitational paths rise into statistical significance, no matter how physically minute they might be. Yet precision always arrives hand in hand with caution, and the scientists themselves emphasize the caveats. What they have derived are not direct measures of mass, but positional residual limits, constraints that describe how far the actual trajectory strays from a gravity-only prediction. These limits define the ceiling of possible acceleration, and when paired with models of gas escape, they generate the debated lower bound estimates for mass. The chain of inference is delicate. It rests on assumptions about rates of gas production, the speed of escape, and the efficiency with which momentum transfers from vapor to nucleus. Alter those inputs, and the derived mass shifts accordingly. The Global Telescope Network offers positions of astonishing accuracy, but translating those raw coordinates into physical properties demands theory and modeling. Even so, the accomplishment deserves recognition. This is acceleration detection brought to the practical limits of ground-based astrometry. In effect, the network has turned Earth into a planet-sized instrument, with baselines stretching across oceans and continents. Each observatory contributes a sliver of sky, and together they assemble a dataset that no single facility could hope to match. This union of perspectives pushes observational science into territory once unthinkable. When positional accuracy sharpens to the point where accelerations of mere billionths of a meter per second squared can be constrained, small bodies cease to be only gravitational test masses. They become laboratories, revealing how momentum conservation sublimation dynamics, and the hidden physics of heat flow shape orbital evolution. This level of rigor explains how researchers could make strong claims about the anomalous nature of 3I Atlas. The acceleration limits tied to it stand among the most exacting ever achieved for any comet or asteroid, native or interstellar. At such fidelity, results that defy expectation demand serious theoretical engagement. And yet, amid the triumph of measurement, the images themselves disclosed a still stranger feature, a cometary tail that appeared to point in the wrong direction. Part 4. The Coma Paradox. On the 21st of July, an image captured by the Hubble Space Telescope brought astronomers to a standstill. Instead of the familiar portrait of a comet-bright nucleus blazing, dust trailing outward in a plume driven away from the Sun 3I Atlas appeared wrapped in a teardrop-shaped cocoon, its glow strangely pointed sunward. This forward-facing antitail defied instinct, unsettling one of astronomy's most reliable patterns. For centuries, observers have trusted that comet tails point away from the sun, carried outward by the combined push of solar radiation and the relentless sweep of the solar wind. Ancient Chinese astronomers once used comet orientations as natural compasses. To see a tail angled directly toward the star itself is to feel the mind strain against intuition, as if gravity and light have momentarily conspired to invert the rules of the sky. Antitails are not wholly unprecedented. In solar system comets, geometry sometimes creates the illusion when Earth's orbital vantage aligns just so, or dust grain dynamics send larger particles along paths that resist radiation pressure while fine dust sails outward. Yet the persistence and clarity of the forward glow around 3I Atlas made it a genuine anomaly. Recent modeling papers propose an explanation rooted in sublimating grain physics and perspective. As ice-rich fragments leave the nucleus, they continue to vaporize while moving outward, and under certain viewing angles this ongoing sublimation produces apparent sunward features. The equations close neatly, but the experience of seeing such a feature remains startling to eyes accustomed to the classic backward-swept tail. Through July and August of the year 2025, the strange glow did not fade. It endured across nights, across instruments, across the gaze of multiple observatories, its resilience arguing against mere perspective trickery. On the 27th of August, Gemini South revealed new layers. Alongside the stubborn forward glow, a more familiar antisolar tail began unfurling, the comet evolving visibly as it approached perihelion. Early frames emphasized forward scattering, while later images revealed the dual structure of material flowing both toward and away from the sunday. This morphing visage carries weight beyond spectacle. The brightness distribution in a comet, determined by dust-to-gas ratios, particle lifetimes, and the tightness of jets, affects the photometric center, the average location of visible light, relative to the actual nucleus. Because astrometric measurements track that photometric centroid, shifts in coma structure risk biasing orbital solutions, potentially fabricating or concealing the non-gravitational accelerations used to infer mass. The task, then, is to disentangle real dynamical forces from photometric illusions. If the nucleus hides within a shifting halo that pulls the light center this way or that, residuals may mimic accelerations that do not exist or obscure ones that do. Analysts must account for such morphology to avoid misjudging the mass and physics of the visitor. Antitails within the solar system generally trace back to known dynamics, but the early strength and lasting presence of the forward glow in 3I Atlas carry us into less charted waters. The modeling community now tests whether ordinary dust dynamics and viewing geometry suffice, or whether something more exotic underlies the spectacle. Into this already complex picture pours chemistry, The James Webb Space Telescope recorded abundant carbon dioxide release, while the Very Large Telescope identified cyanogen and nickel emission lines without the accompanying iron expected in standard comet spectra. The combination is perplexing. Enriched carbon dioxide, nickel divorced from iron, and dust morphology at odds with template behavior. Nickel in comets is not unheard of, but its appearance in isolation is unusual. Typically, nickel and iron emerge together, birthed in similar nucleosynthetic processes, residing in related mineral matrices. Their separation hints at strange formation environments or selective release mechanisms unknown to most comets. These chemical signatures may tie back to the morphological riddle, linking composition to structure, gas to glow. If 3I Atlas carries minerals laced with unusual metals or organic compounds, their differential sublimation could spawn dust populations unlike those of ordinary comets, each with distinct optical and dynamic properties. The result would be a cometary cloak that behaves in ways unanticipated by current models, a spectacle in which physics, chemistry, and perspective converge to produce an interstellar visitor that looks familiar, yet refuses to play by familiar rules. Visual metaphors help untangle the mystery of the antitale for audiences not versed in scattering physics. Picture animated vectors, showing the sun's direction contrasted with the apparent orientation of a comet's tail, perspective altering the geometry until the relationship between source and debris seems to reverse itself. Watching a three-dimensional process from the fixed viewpoint of Earth can create optical illusions that unsettle physical intuition. The forward glow of 3I Atlas may result from sunlight scattered by dust grains of particular sizes and compositions. When such grains scatter light preferentially in the forward direction, toward the observer rather than away from the sun, the brightness appears to defy the basic rule that tails stream outward. The effect is genuine, but its interpretation demands a framework grounded in scattering theory, particle distributions, and composition. Even so, astronomers remain cautious. Antitails have been seen in solar system comets for decades, and none has overturned the fundamentals of dust dynamics. The striking persistence of the forward glow in this case may signal vigorous activity or dust grains with unusual physical properties, not a complete rewriting of physics. The balance between dust and gas influences not only appearance, but also the calculations that anchor mass estimates. If 3I Atlas emits a greater ratio of dust to gas than ordinary comets, or if its dust grains differ in size and substance, then the relationship between visible outflow and expected non-gravitational acceleration could shift dramatically. To probe this balance, astronomers combine multiple tools. Visible images capture scattering patterns and coma morphology. Infrared spectra chart thermal properties and gas emissions. Radio telescopes trace molecular transitions that reveal gas production directly. Integrating these datasets into coherent models stretches the ingenuity of observers and theorists alike. Hubble, Gemini South, and other facilities have supplied time series imagery, documenting the comet's changing shape as it warmed in its approach. Different volatiles awaken at different solar distances. Water ice activates at around 3 astronomical units, carbon dioxide much farther, while exotic ices respond at their own thresholds. This staged sublimation drives shifting dust entrainment, and the comet's evolving form reflects the chemistry of its awakening. The visual metaphor that best captures the paradox is snowfall in reverse, as though flakes were drifting toward the sun instead of away. The mind resists the image because it inverts ordinary expectation of how debris responds to force. When tails point sunward, they confront the foundations of how we believe matter must behave in space. This coma paradox has become shorthand for Atlas's defiance, layering on top of its anomalous mass and exotic chemistry a morphology that seems to run backwards. Each observation adds complication rather than resolution, pushing astronomers deeper into uncertainty. But perhaps the most unsettling question grows from its suspected bulk. If preliminary estimates prove true that 3I Atlas weighs at least 33 billion tons and conceals a nucleus 5 kilometers or more in diameter, then it is a statistical outlier of stunning proportions. Population models predict smaller bodies should dominate the sample of interstellar visitors. By logic alone, we ought to have found dozens, if not hundreds, of lesser wanderers before encountering one so immense. Consider the mechanics of ejection. Planetary systems cast debris into interstellar darkness through gravitational encounters with giant planets, through stellar flybys that destabilize outer reservoirs, or through resonant instabilities in protoplanetary disks. In each plausible scenario, lighter fragments escape more easily than monoliths. Less mass requires less energy to fling free, so smaller objects should vastly outnumber giants adrift in the interstellar medium. Detection biases should also tilt discovery toward the smaller end. The tiniest grains remain invisible, but bodies from 100 meters to a kilometer in scale ought to reveal themselves when they graze the inner solar system and sprout bright comae. Yet the third interstellar object ever found may be the largest, its presence casting doubt on the demographic frameworks astronomers have built. 3I Atlas, with its dazzling antitail, its strange chemistry, and its staggering mass, appears intent on reminding humanity that the universe still keeps secrets close, and that even in the age of space telescopes, each revelation can overturn the expectations of a field. The reality that our first 3 confirmed interstellar visitors span such a vast range in mass, from Oumuamua with its estimated millions of tons to 3I Atlas with its suspected tens of billions, challenges simple statistical expectations and unsettles the imagination. One explanation may lie in observational selection effects. Only in recent years have wide-field surveys such as ATLAS and the Catalina Sky Survey reached the sensitivity and sky coverage needed to routinely notice such fleeting guests. The Vera Rubin Observatory, destined to transform transient astronomy, has only just begun operations. We may be sampling the population with crude tools, seeing only the tip of a far larger iceberg. Detection order could reflect coincidence in geometry rather than true rarity. 3I Atlas approached along a trajectory aligned with the ecliptic plane, the band where most planetary bodies travel, and that fortuitous alignment made it easier to find and follow than objects cutting across the sky on highly inclined orbits. Its favorable geometry may have compensated for the normally low odds of catching such a massive interstellar fragment. Another interpretation holds that our knowledge of ejection mechanisms is incomplete. Perhaps some stellar nurseries preferentially launch large objects into space, or perhaps small debris is ground down or destroyed more efficiently on the long voyage between stars. Cosmic rays may erode fragile surfaces. Dust collisions may fracture and pulverize weaker pieces. Chance encounters with other stars may bake or stress them into oblivion. If fragments smaller than a few hundred meters cannot survive million-year odysseys, then only the stronger, larger remnants remain to be caught in our telescopes. This fragility hypothesis deserves careful thought, for it would bias the population that actually arrives here toward giants. Yet even allowing for these destructive filters, 3I Atlas remains awkwardly placed within statistical models. Population synthesis methods that explain asteroid belt structure and Kuiper belt demographics falter when asked to justify such a heavyweight arriving so soon in our census. Either the models require revision, or three-eye atlas, is a true rarity that appeared precisely when humanity opened its eyes wide enough to see. Historical context sharpens the perspective. The discovery of Oumuamua in 2017 began this field, a needle-shaped wanderer that baffled interpretation. 2Y. Borisov followed in 2019, behaving like a familiar comet, and reassuring astronomers that some interstellar guests mirrored the bodies born in our own solar system. Now, in 2025, comes Three-Eye Atlas, completing a set of three statistically useless for broad conclusions. It is like trying to infer the distribution of human heights after measuring only three people, one short, one average, one a towering giant. Outliers dominate inference when the sample is that small. Survey mathematics offers hope. The Rubin Observatory's legacy survey of space and time will scan the southern skies every few nights for a decade, potentially discovering hundreds or even thousands of such visitors. If Atlas represents a typical mass, Rubin will find more giants. If Atlas is a fluke, Rubin will return an avalanche of smaller specimens, and statistical patterns will emerge with clarity. Beyond mere curiosity, the stakes touch the foundations of planetary science. If bodies like Atlas prove common, models of stellar system formation must explain how such titans are ejected with relative ease. Current theory emphasizes planetary migration and gravitational scattering in early system chaos, mechanisms thought to expel primarily smaller fragments. If instead Atlas is genuinely unique, its survival and size hint at unusual birthplaces or protective mechanisms, clues to processes still hidden even within our own solar system. The reservoir problem leads deeper into galactic astrophysics. Stars form in clusters, tugging at each other, scattering debris across parsecs. The efficiency of these interactions, multiplied by the rate of star formation across cosmic time, dictates how many interstellar wanderers should drift through any cubic parsec of space. Current estimates suggest billions of objects, larger than 100 meters, inhabit each cubic parsec of the local medium. They remain unseen until proximity to the Sun ignites coma, or until reflected sunlight betrays their passage. Bridging the gap between theoretical counts and observed specimens is the task ahead. Responsible science demands humility. Mass estimates for Atlas may rest on premature assumptions. Observed statistics may reflect biases rather than deep truths. Yet this uncertainty is the pulse of discovery. We are watching astronomy wrestle with unanticipated realities. Whether Atlas proves typical or anomalous, it forces questions about how matter moves between stars and what those journeys reveal about galactic evolution. The problem of tiny sample size will eventually fade. Within a decade, surveys will provide dozens or hundreds of examples. Statistical noise will yield to demographic clarity. For now, Atlas stands alone, an ambassador carrying information about environments alien to our own, conditions we can scarcely model. Its strange combination of mass, morphology, and chemistry acts as a riddle meant to sharpen our methods and broaden our theories. The uncomfortable truth remains that if our first detections skew so heavily toward the massive end of the spectrum, something crucial is absent in our understanding of interstellar debris. The question is whether the missing element is hidden in observational biases, theoretical gaps, or physics we have not yet grasped, operating in the silent reaches between stars. Before we resolve the statistics, we must first refine the ejection and reservoir models that underpin them. Atlas demands nothing less than a re-evaluation of what kind of debris stellar systems release into the galaxy, and how those relics survive the cold eternity of interstellar space. Part 5. The Interstellar Reservoir Problem. The galaxy functions as a vast redistribution network for planetary debris, with stellar systems continually casting material outward that then drifts between the stars, seeding the raw stock from which interstellar visitors emerge. To grasp this cosmic recycling process, theorists model three main ejection pathways: planet-to-planet gravitational scattering, close stellar flybys, and instabilities in protoplanetary disks around newborn stars. Among these, planet-to-planet scattering dominates present frameworks. In the turbulent infancy of planetary systems, giant bodies migrate and interact chaotically, striking smaller comets and asteroids like cue balls on a cosmic billiard table, sending some careening onto hyperbolic escape routes. Physics favors the lightweights here. Launch velocity scales inversely with mass, so smaller fragments are accelerated far more easily than hulking giants. A planet the size of Jupiter can hurl kilometer-scale comets into interstellar space with relative ease, but to launch something the size of 3I Atlas requires extraordinary alignments and energy transfers, events far less probable than routine scattering of smaller bodies. Stellar flybys add another avenue of escape, especially in dense clusters where stars are born close together. When one star passes within a few hundred astronomical units of another's planetary system, its gravity can destabilize the outskirts, flinging resident objects into interstellar exile. The effectiveness depends on flyby velocity, closest approach, and the configuration of the target system's outer architecture. Because stellar masses dwarf planetary ones by factors of hundreds or even thousands, these encounters can expel far larger bodies. A solar mass star brushing past could theoretically eject objects weighing billions or tens of billions of tons, making this mechanism plausible for producing behemoths like 3I Atlas. The third pathway emerges earlier still. In the first few million years of stellar evolution, before planets have fully taken shape, protoplanetary disks sometimes suffer gravitational instabilities. Spiral density waves and asymmetric structures in these gas-rich, dust-heavy disks can scatter embedded material outward. Such disk-driven ejections occur only during the brief window before disks dissipate, but if effective, they could seed interstellar space with massive bodies early in a system's life. The question remains which mechanism dominates under what conditions, and how each contributes to the observed size spectrum of wanderers. The answer likely varies across stellar environments: young clusters versus isolated field stars, metal, rich versus metal, poor systems, binaries, compared with single stars. Each context imprints different signatures on the debris it ejects. Yet observational constraints remain painfully thin, with only 3 confirmed interstellar objects: Oumuamua, 2I Borisov, and 3I Atlas. Uncertainties in population demographics span orders of magnitude. It is statistically meaningless to infer distributions when a single outlier can distort the entire picture. The commissioning of the Vera Rubin Observatory has already delivered glimpses of Atlas, foreshadowing a transformation. Rubin's wide-field camera and rapid cadence will soon sweep the entire southern sky every few nights, detecting dozens if not hundreds of interstellar visitors each year. Such a flood will elevate population studies from conjecture to empiricism within a decade. Current reservoir models attempt to connect these ejection processes with observed properties, tracking the accumulation of interstellar debris across galactic timescales. Star formation rates, cluster dynamics, and planetary architectures combine to set how much material of each size should populate the interstellar medium. These models nearly all agree on one principle: small bodies should vastly outnumber large ones. Steep size distributions imply that kilometer-scale wanderers ought to be rare compared with 100-meter fragments. Yet Atlas seems to defy that rule. The lifetime of protoplanetary disks intensifies the puzzle. Such disks typically disperse within 5 to 10 million years, stripped by stellar radiation or consumed by accretion. That narrow window limits the time available for disk instabilities to scatter large objects. If giants like Atlas originate from disk-driven events, they must both form and depart before the disk vanishes, demanding extraordinary timing. Potential resolutions to the paradox range from survivorship bias, which may erase smaller debris during long interstellar journeys, to detection geometry, which might make certain giants more visible, to dust-rich comae that amplify apparent brightness and increase discovery odds. Each possibility offers partial answers, yet none eliminates the fundamental dissonance between theory and observation. Atlas, looming as both anomaly and ambassador, continues to pressure models into revision, forcing astronomers to rethink how stellar systems release their debris into the dark sea of the galaxy. Each possible explanation alters the fragile relationship between what we observe and what actually exists in the galactic population of interstellar debris. Survivorship bias could operate through differential erosion rates as objects endure the long exile of interstellar transit. Cosmic ray bombardment might steadily strip away fragile surfaces. Sublimation triggered by random stellar flybys could fracture small nuclei. Collisions with drifting interstellar dust grains might grind weaker fragments into invisibility. Across the million-year timescales required for travel between stars, such forces would preferentially destroy the fragile and the small. If only the robust, massive specimens endure, then the population that actually arrives in our skies is biased toward the giants. Detection geometry adds another skew. Visitors like 3I Atlas, approaching near the ecliptic plane, enjoy favorable circumstances, extended visibility windows, simpler tracking, and a geometry that aligns with the strengths of existing survey telescopes. By contrast, objects with highly inclined or retrograde paths may slip through unnoticed, underrepresented in current statistics not because they are rare, but because we are blind to them. Dust production introduces yet another distortion. A comet that generates copious dust appears far brighter than its nucleus alone would suggest. This enhancement raises its detectability at great distances. If Atlas produces more dust per unit surface than typical comets, then it may have announced itself earlier and louder than less active siblings, skewing the record toward anomalously bright visitors. The conservative scientific posture treats such anomalies not as conclusions, but as prompts for better data. 3 examples provide no statistical muscle. Extraordinary claims about demographic surprises demand extraordinary evidence, and the current record is far too thin. Yet the challenge cannot be dismissed. Should future surveys confirm that massive interstellar objects arrive more often than reservoir models predict, then theory must adapt, revising either the efficiency of giant body ejection or the production rates in their source environments. The stakes extend beyond mere census. Ejection mechanisms and survival rates illuminate how planetary systems form and evolve. The wandering debris carries within it records of conditions in stellar nurseries across galactic history. Population synthesis frameworks attempt to weave these threads together, linking star formation rates, cluster dynamics, planetary architectures, and ejection efficiencies into predictions of how many wanderers of each size should pass through the solar system. Current forecasts range widely, reflecting the uncertainty of their assumptions. Some predict encounter rates of roughly 1 per year for bodies larger than 100 meters, others an order of magnitude higher or lower. Atlas and its 2 predecessors are the first anchors on these drifting projections, The reservoir problem ultimately connects local observations to galactic processes unfolding over billions of years. Each interstellar visitor is a messenger, bearing silent testimony about stellar environments we cannot visit. As surveys multiply and detections accelerate, population studies will harden from speculation into precision. Atlas's apparent anomalies may fade as early noise or stand as signs of deeper truths about the movement of matter between stars. But before those patterns resolve, astronomers must wrestle with an even stranger twist: the unexpected chemistry of Atlas, nickel glowing without the companion's signature of iron. Part 6. The Nickel Without Iron Mystery. Spectroscopy from the Very Large Telescope uncovered one of the most puzzling traits yet in the coma of 3I Atlas: strong nickel emission lines blazing in the infrared, while iron remained conspicuously absent. This asymmetry defies one of the simplest assumptions in comet chemistry, that iron and nickel appear together because they share stellar origins and often occupy the same compounds in meteoritic material. The observation was straightforward, the implications anything but. During August of the year 2025, the telescope's high-resolution spectrographs clearly registered several atomic nickel transitions in the 700 to 900 nanometer range. These lines stood well above background noise, strong enough to permit quantitative estimates of nickel production rates and spatial distribution. Iron lines, which should have appeared at neighboring wavelengths, were not simply weak, they were missing. The spectra established upper limits on iron emission far below what is routinely detected in solar system comets at comparable solar distances. This was not an absence by chance, but a genuine peculiarity demanding explanation. Context sharpens the surprise. In astronomical settings, iron and nickel usually travel together, born from similar nucleosynthetic pathways in stellar interiors and intermingled within the minerals of primitive bodies. To witness nickel alone is like walking into a forest where oak trees flourish yet maples are nowhere in sight, in a region where both should grow. Derived production rates told their own story. As Atlas drew closer to the Sun, both nickel and cyanogen emissions rose steeply, following power law relationships with exponents near -8 or -9. Such scaling betrays a sharp temperature dependence, pointing to processes that switch on near a thermal threshold. Solar heating seems to unlock nickel atoms from the surface suddenly, driving them into the coma where they radiate in the infrared. The mathematics of that temperature dependence hint at exotic mechanisms beyond simple sublimation. Traditional comet models struggle here. Direct evaporation of nickel-bearing minerals requires temperatures far higher than those reached during the observations. Another pathway must be active. Photon-stimulated desorption offers one candidate. Ultraviolet radiation from the sun can snap chemical bonds, freeing atoms otherwise locked within mineral matrices. If Atlas's nucleus contains nickel compounds more vulnerable to photodesorption than iron phases, that could explain the selectivity. Other ideas turn to organometallic chemistry. Complexes such as metal-carbonyl compounds can break apart at relatively low temperatures, releasing metal atoms through chemical decomposition rather than outright mineral vaporization. If nickel naturally forms more volatile complexes than iron in the icy chemistry of Atlas's birthplace, that differential could yield the strange pattern now observed. The mystery deepens when paired with results from the James Webb Space Telescope. Webb detected a coma dominated by carbon dioxide, with unusually high ratios of carbon dioxide to water, suggesting formation in the far reaches of a stellar system beyond the carbon dioxide snowline. In such frigid environments, exotic ice phases and unusual metal-rich compounds might condense, embedding nickel-bearing volatiles in the nucleus. Preserved across eons of interstellar travel, They would emerge only when heated during a solar flyby, producing the unusual nickel spectrum. This view paints Atlas as a chemical time capsule, carrying fingerprints from alien birthplaces billions of years old. What this chemistry does not indicate also deserves clarity. Some media voices leapt upon the nickel without iron pattern to suggest technological interpretations, noting its resemblance to certain human alloys. Such claims lack any grounding. Atomic emission lines reveal natural processes, not engineering. Metallic lines in cometary comae result from photophysics, not metallurgy. The lesson here is as much about media literacy as about astrophysics. While peer-reviewed studies focus on desorption thresholds and complex chemistry, social channels amplified narratives of artificiality without evidence. The true marvel lies not in imagined technology, but in genuine alien chemistry, a natural composition so rare that it challenges our frameworks. 3I Atlas once more reminds us that interstellar visitors carry surprises, its spectral fingerprint underscoring how little we know of the materials that condense in distant planetary nurseries, and how extraordinary the opportunity is to study them as they briefly light our skies. The Very Large Telescope team presented their spectroscopic results as striking but natural chemistry, not as evidence of engineered artifacts disguised as comets. The distinction between genuine anomalies worthy of scientific scrutiny and sensational misinterpretations that fuel public speculation underscores how astronomy truly works. Unusual chemistry demands explanation, but unusual does not equal artificial. The cosmos offers countless natural pathways capable of producing abundance patterns that at first glance seem improbable. History within solar system comet research provides parallels. Several comets once revealed puzzling metal emissions with odd ratios that confounded early investigators, only to be resolved later through detailed studies of grain composition, thermal effects, or photochemical processes. This is the rhythm of science. Hypotheses proposed, predictions tested, explanations refined as new data arrives. The nickel emission lines from 3I Atlas offer far more than curiosity. They set quantitative constraints on gas production rates and coma temperatures. The widths of the spectral lines measure thermal broadening and bulk motion velocities, while intensity ratios between lines pin down excitation conditions and density profiles. Such measurements feed directly into physical models of coma evolution, anchoring theory to data. To visualize the observations, imagine a spectrum with wavelength stretched across the horizontal axis and brightness rising vertically. At precise positions corresponding to nickel's atomic transitions, sharp peaks rise, unmistakable signatures of emission. Where iron should appear, the spectrum remains flat, signals sinking to noise. This absence stands out more vividly when graphed than when described. Spatial distribution adds another dimension. If nickel emissions originate from discrete vents or active spots on the nucleus, then high-resolution spectroscopy should reveal localized structures. If instead the source is distributed grain processing, the emission should smear into a more uniform halo. Current instruments cannot resolve this level of detail, but future extremely large telescopes will map comae with the spatial and spectral fidelity required to discriminate between these scenarios. Temporal behavior promises further clues. As Atlas arcs toward perihelion, nickel emissions will respond to increasing solar energy. If photodesorption drives the process, emission rates should track solar flux closely. If thermal mechanisms dominate, the curve will follow surface heating, lagging by intervals set by thermal conduction through surface layers. Observing such trends transforms puzzling anomalies into diagnostic tools. Metal emissions are more than chemical novelties. They probe the inventory of refractory elements and the processes that release them, offering windows into primordial matter preserved from planetary system birth. Understanding these emissions informs our knowledge of early solar conditions and distant stellar nurseries alike. The nickel without iron pattern exemplifies how Atlas continues to resist conventional expectations. From its extraordinary mass to its strange morphology to its chemical eccentricities, this interstellar visitor insists on pushing astronomy into uncomfortable territory. Yet history shows that persistent anomalies are engines of progress, forcing reconsideration of assumptions and the invention of new frameworks. Oumuamua provoked years of debate, generating a flood of papers and targeted campaigns. Atlas is already following that pattern, its mysteries catalyzing improvements in both observation and theory. Whether the eventual explanation rests on mundane physics or on processes not yet imagined, the comet's peculiarities have already expanded the frontier of interstellar chemistry. Puzzles such as this energize the field, reminding us that science thrives on the unexpected. But persistent surprises also invite voices that step beyond data into speculation, raising the question of what happens when someone insists these anomalies must point toward technology rather than nature. Part 7. The Technological Hypothesis. The technological interpretation of 3I Atlas represents testable scientific hypothesis generation, not evidence-free assertion. Proponents present calculations, orbital analyses, and observational predictions that can be evaluated through standard scientific methods. The cultural context surrounding these discussions reflects broader societal fascination with potential evidence for extraterrestrial intelligence. Following decades of SETI searches and recent governmental acknowledgements of unidentified aerial phenomena, public interest in possible technological artifacts runs high. This enthusiasm can both motivate scientific investigation and distort interpretation of ambiguous data. Responsible science communication requires presenting multiple hypotheses while maintaining appropriate levels of confidence in different explanations. The technological interpretation deserves mention as one possibility among several, but current evidence remains insufficient to favor it over more conventional alternatives involving unusual but natural comet physics. The media amplification cycle demonstrates how scientific speculation can evolve into definitive claims through repeated reporting and social media sharing. Initial papers presenting technological possibilities as hypotheses, requiring further investigation, become transformed into assertions about probable artificial origins through successive retellings that lose important caveats and hypotheses, uncertainties. Educational opportunities arise from these discussions about hypothesis testing, statistical reasoning, and the scientific method. 3. iAtlas provides a real-time example of how scientists approach unusual observations, generate multiple explanations, design tests to distinguish between alternatives, and refine understanding as new data accumulates. The peer review process plays crucial roles in evaluating unconventional claims. While preliminary analyses and conference presentations can explore speculative ideas, definitive conclusions require rigorous evaluation by expert reviewers who examine methodology, statistical analysis, and interpretation of results. This quality control mechanism helps separate legitimate scientific inquiry from unfounded speculation. Future observations will provide decisive tests of the technological hypothesis through continued astrometric monitoring, spectroscopic analysis, and potential spacecraft encounters. If 3I Atlas exhibits behavior consistent with natural comet physics, technological interpretations will fade. If observations reveal genuinely anomalous characteristics, the hypothesis gains credibility and motivates more detailed investigation. The timing of these definitive tests spans the next 18 months, as 3I Atlas completes its passage through the inner solar system and emerges from behind the Sun for continued Earth-based observations. This extended observational campaign provides multiple opportunities to test predictions from both natural and artificial origin scenarios. Regardless of ultimate conclusions, the technological hypothesis discussion highlights the importance of keeping open minds while maintaining rigorous standards for evidence evaluation. Science progresses through willingness to consider unconventional possibilities while demanding extraordinary proof for extraordinary claims. But there's another speculative framework that's equally fascinating and potentially more scientifically grounded. The possibility that objects like 3I Atlas serve as planet formation seeds. The technological interpretation of 3I Atlas represents not wild assertion but the structured process of generating hypotheses that can be tested. Its proponents rely on orbital calculations, probabilistic arguments, and observational predictions that fall squarely within the machinery of scientific method. What surrounds the debate, however, is a cultural context charged with fascination for extraterrestrial intelligence. After decades of listening campaigns in the search for extraterrestrial intelligence, and in the wake of governmental acknowledgements of unidentified aerial phenomena, the public appetite for signs of technology beyond Earth is especially keen. That enthusiasm can spur investigation, but it can also bend ambiguous data into premature conclusions. Responsible communication requires balance. The technological perspective deserves mention, but only as one of several possible explanations. The weight of evidence at present favors natural, though unusual, cometry processes over extraordinary engineering. The cycle of media amplification shows how nuance erodes. A speculative paper that proposes artificiality as one hypothesis among many can, through successive retellings across headlines and social platforms, become transformed into a proclamation of artificial origin, stripped of its caveats. The result misleads, turning science's openness into apparent certainty. Yet these debates also offer educational opportunities. Atlas provides a vivid case study in how scientists confront anomalies. They generate alternatives, test them with predictions, and refine their models as data accrues. It is the scientific method in real time. Peer review serves as safeguard, filtering bold ideas through expert scrutiny of methods, statistics, and interpretations, separating the fertile from the fanciful. Preliminary analyses and conference talks may explore wide possibilities, but firm conclusions require the discipline of formal evaluation. The path forward lies in continued observation, astrometric tracking, spectroscopic surveys, and perhaps even spacecraft investigations will test the predictions of both natural and technological frameworks. Should Atlas conform to expected comet physics, the artificial conjecture will wither. If it resists explanation, the hypothesis will gain weight and demand deeper pursuit. The critical window spans the next 18 months, as Atlas arcs through perihelion, vanishes into solar glare, and then re-emerges for Earth-based study. Each phase offers new data that will either narrow or widen the interpretive field. Whatever the verdict, the discussion underscores an essential principle. Science thrives on openness to possibility paired with rigor in proof. Unconventional ideas should be entertained, but extraordinary claims require extraordinary evidence. And as that principle holds, another speculative framework has begun to take shape, one that does not invoke technology, but rather hints at Atlas as a natural seed of planetary formation itself. Part 8. The Planet Seeding Hypothesis. Suzanne Falsner's planet seeding hypothesis stands out as one of the most provocative frameworks for explaining why massive interstellar wanderers like 3I Atlas might matter far beyond curiosity. Her idea proposes that when such bodies are captured by young stellar systems, they could bypass traditional bottlenecks in planet formation and ignite giant planet growth during the fleeting window when protoplanetary disks still carry the mass required for runaway accretion. The standard paradigm of core accretion has long faced a timing problem. Gas giants must bulk up quickly before their birth disks evaporate under stellar radiation or feed themselves into the central star. Observations suggest that disks survive only between 5 and 10 million years, which leaves little time for planetary cores to cross the critical threshold where gravity snowballs gas and dust into world-sized envelopes. The obstacle becomes sharper at the so-called meter-size barrier. At this stage, growing planetesimals interact so strongly with disk gas that they spiral inward and vanish before they can assemble into larger, stable bodies. This aerodynamic drag acts like a cosmic conveyor belt, feeding small debris into the stellar furnace, erasing the building blocks before planets can fully form. The capture of interstellar objects offers a graceful escape route. If a nascent system intercepts kilometer-scale wanderers already forged in distant stellar nurseries, these bodies could arrive as ready-made seeds. With mass sufficient to resist drag, such visitors would not only endure the disk environment, but also serve as gravitational scaffolds, sweeping up local material at accelerated rates. In this view, an object like Atlas is not a rogue intruder, but a potential catalyst, triggering worlds to form faster than local debris alone would allow. At the European Planetary Science Congress and the Division for Planetary Sciences meeting in the year 2025, researchers presented simulations that breathe life into this scenario. The models indicate that more massive stars excel at capturing interstellar debris, a result that resonates with the observed correlation between stellar mass and the likelihood of hosting giant planets. The mechanism is gravitational focusing. Large stars sculpt deeper potential wells, expanding their capture cross-sections, while their birth in dense stellar clusters increases encounter rates during the critical disk phase. In this setting, the galaxy becomes a churning marketplace where stars trade planetary seeds across interstellar distances. Recent popular coverage has highlighted this concept, stressing that seeding by captured wanderers complements rather than replaces traditional core accretion. Both pathways may operate in parallel, with the balance shifting according to environment. Chemistry strengthens the case further. Observations by the James Webb Space Telescope revealed a coma rich in carbon dioxide, with abundance ratios implying formation in regions colder than -125 degrees Celsius, far beyond the carbon dioxide snowline of its parent star. Such icy origins point to distant stellar peripheries, exactly the kind of environments that might export volatile-rich seeds. Should a captured visitor deliver these exotic ices into a new disk, it could infuse alien chemistry into forming planets, enriching the variety of atmospheric compositions now being catalogued in exoplanet surveys. In this way, Atlas exemplifies the potential for interstellar mixing, with each captured body adding both gravitational heft and chemical novelty. Evaluating whether seeding truly matters requires population statistics on interstellar debris, a field still in its infancy, but rapidly advancing as surveys sharpen their reach. If the legacy survey of space and time uncovers dozens or even hundreds of interstellar visitors over the next decade, capture scenarios in young stellar systems shift from speculation to statistical plausibility. Conversely, if 3I Atlas proves to be an exceptional rarity, then planet seeding hypotheses weaken under the weight of insufficient raw material. The credibility of seeding depends not only on isolated anomalies, but on whether the galaxy produces these visitors in numbers capable of altering planetary birth stories. Theoretical efforts already suggest that young stellar systems could capture interstellar bodies at rates high enough to influence formation outcomes. Dense star-forming regions combine frequent encounters with passing debris and gravitational landscapes conducive to capture. This process works best in the opening few million years, when circumstellar disks still hold enough gas and dust to feed rapid growth around captured cores. The seeding idea is not new, but recent models have given it sharper edges. Early proposals envisioned the possibility of outside seeds decades ago, but lacked detailed calculations. Now simulations describe capture rates, size distributions, and evolutionary tracks with increasing resolution. Some results are startling. Prior work proposed that as many as 10 million or more Oumuamua-scale seeds could be present per protoplanetary disk during peak formation epochs, a suggestion that would radically rewrite the timeline of giant planet assembly. Capture efficiency hinges on familiar variables: the relative velocity of the interstellar body to the target system, the structure and mass of the disk, and whether the system resides in a binary or cluster environment that modifies gravitational interactions. Each factor influences not only the likelihood of capture, but also the fate of the captured object. Different environments therefore produce different seeding signatures, an echo of cosmic geography stamped into planetary demographics. Yet counterarguments remain formidable. Capture represents only the first step. Once inside, a seed must endure. Tidal disruption, gravitational kicks from larger bodies, and migration through unstable disk regions can erase the advantage of capture. Disk evolution itself complicates matters further. Protoplanetary disks do not remain static backdrops. They churn and thin, reshaping density profiles, temperature gradients, and turbulence. These shifting landscapes might shepherd captured seeds into favorable orbits or scatter them to oblivion. Testing such scenarios requires magnetohydrodynamic simulations that marry fluid physics with gravity, chemistry, and thermodynamics across many scales, an endeavor straining the edge of current computational capacity. Observational signatures of seeding remain almost entirely theoretical. Perhaps captured seeds imprint chemical or isotopic anomalies on the atmospheres of mature exoplanets, but detecting such faint signals exceeds the reach of present instruments. Instead, researchers look to exoplanet demographics for indirect evidence. If seeding processes matter, then statistical fingerprints should appear in the distributions of planetary masses, orbital architectures, and host star correlations catalogued in large surveys. Patterns may already lurk within existing datasets, waiting for sharper interpretation. Here, the distinction between firm prediction and speculative extrapolation matters. Capture cross-sections and gravitational focusing are well-understood physical effects, while survival and growth within evolving disks remain highly uncertain. Visual representations help. One can imagine animations where an interstellar object plunges into a gas-rich disk, loses energy through drag, spirals inward until its orbit circularizes, and then begins sweeping up surrounding matter. The physics is core accretion with a head start, the timeline compressed by the mass the seed carries with it. The advantage becomes clear when compared with the conventional story. Building kilometer-scale planetesimals from dust grains can consume millions of years, during which many fragments succumb to aerodynamic drag. But if a stellar nursery captures kilometer-scale seeds already built elsewhere, the growth clock resets with maturity already achieved, enabling rapid progression to giant planet thresholds. Future theoretical work must refine these capture rate predictions and survival probabilities. That requires merging stellar cluster dynamics, models of interstellar object populations, and detailed protoplanetary disk physics, a multi-scale puzzle that demands new computational strategies. Atlas itself serves as a test case. Its anomalous properties make it a natural candidate for exploring whether massive wanderers could plausibly act as planetary seeds. If similar objects prove common, then seeding joins the canon of plausible formation pathways. If such giants remain outliers, then conventional core accretion and disk instabilities continue as the dominant frameworks. Yet, the implications stretch beyond individual worlds. If seeds pass freely between stellar systems, the galaxy itself becomes a conveyor of matter and chemistry, weaving a shared evolutionary thread across distances measured in light years. Seeding may represent not only a mechanism of planet formation, but a form of cosmic communication, mixing the ingredients of worlds between stars. That possibility raises profound questions about the uniqueness of planetary systems. Are the chemical fingerprints we observe in exoplanet atmospheres solely the product of local birthplaces, or mosaics of alien contributions delivered across the gulfs of space? Whatever the eventual verdict, the discoveries of this decade emphasize timing. Why are we detecting such massive interstellar bodies now, at the very dawn of systematic surveys? Part 9. The Cosmic Timing Puzzle. The discovery and characterization of 3I Atlas exemplify the confluence of technological maturity, geometric good fortune, and cosmic coincidence, a rare alignment of circumstances that explains why such a massive interstellar visitor has been detected now rather than earlier. To understand this timing, one must examine the revolution in observational infrastructure, the geometric pathways that brought the object into our view, and the delicate line between statistical fluctuation and genuine physical novelty. The observational architecture enabling Atlas's discovery reached full stride only within the past few years. The Atlas network expanded southward in the year 2022, with installations in Chile complementing the original Hawaiian facilities. Together, these sites provided near-continuous sky coverage, taking advantage of Earth's rotation to pass the baton from hemisphere to hemisphere. Automated pipelines accelerated detection to follow up within hours rather than weeks. When the Chilean node spotted Atlas on the 1st of July in 2025, the Minor Planet Center flagged it as noteworthy within days. By the 21st of July, the Hubble Space Telescope had already captured images, and by early August, the James Webb Space Telescope recorded infrared spectra. This choreography marked a quantum leap in responsiveness, unimaginable just a decade earlier. Yet technology alone did not secure discovery. Geometry played a decisive role. Atlas approached along a trajectory almost aligned with the ecliptic plane, its orbital inclination measured at just over 4 degrees. Survey telescopes naturally concentrate on this zone, where most asteroids and comets reside. An object arriving from a steeply inclined or retrograde orbit would have been far more difficult to detect, slipping outside the optimized fields of view. Thus, Atlas's alignment effectively boosted its odds of discovery, raising the possibility that our growing catalogue of interstellar visitors may be biased towards such geometrically favorable arrivals. Meanwhile, mass estimates based on non-gravitational acceleration limits attracted immediate attention, with headlines trumpeting the possibility of a tens of billions of tons nucleus. Yet such numbers rest on assumptions about outgassing physics that remain under refinement. Responsible communication distinguishes preliminary inference from confirmed result, but the cycle of media amplification often compresses nuance into certainty. Here Atlas serves as a case study in how active research becomes simplified through repeated reporting until hypothesis morphs into claim. spacecraft perspectives promise to break through observational gaps. As Atlas sweeps behind the Sun during its perihelion passage between late September and early November, ground-based observatories lose visibility, but the Parker Solar Probe's WHISPER instrument may glimpse the object from vantage points unavailable to Earth. Such solar-side perspectives could resolve the ongoing riddle of the sunward glow and the evolving dual-tail morphology, phenomena that ground-based telescopes have struggled to interpret cleanly. Observing Atlas near perihelion from multiple geometries will prove crucial to separating physical processes from viewing artifacts. The sample size problem looms over all these debates. With only 3 interstellar visitors, Oumuamua, Borisov, and Atlas, statistical inference about population characteristics is essentially meaningless. Small number statistics often produce misleading impressions, anomalies that fade once larger datasets accumulate. Atlas may represent nothing more than a statistical unicorn, a rare giant from the far tail of the interstellar size distribution that happened to cross our path just as systematic surveys began in earnest. Hardware advances explain why such unicorns now emerge. Adaptive optics sharpen images from ground-based observatories by correcting for atmospheric turbulence. Space telescopes remove atmospheric absorption entirely. Detector technologies push efficiency higher while reducing noise. These improvements expand the window of detectability, revealing populations that once remained hidden. The appearance of massive interstellar visitors may reflect not a sudden surge in cosmic traffic, but a new ability to see what was always there. Equally transformative has been the evolution of survey strategy. Observing cadence, sky coverage, and data analysis algorithms have all been tuned to maximize discovery rates. Rapid coordination between facilities ensures that transient detections are confirmed and characterized quickly, preventing objects from slipping away unstudied. This ecosystem of surveys and follow-up telescopes now functions as a global nervous system for transient astronomy. At its center, the Vera Rubin Observatory looms as the next leap. Its legacy survey of space and time will scan the entire southern sky every few nights for a decade, promising not just a handful but hundreds, perhaps thousands, of interstellar detections. Population statistics will graduate from speculation to empirical science. The implications extend beyond catalogues. If massive wanderers like Atlas prove common, the scientific community must develop protocols for rapid response, coordinated observing campaigns, dedicated funding streams, even spacecraft missions on standby. The infrastructure assembled for Atlas offers a blueprint, a rehearsal for a future in which interstellar objects arrive regularly at our doorstep. What appears as coincidence today may soon become routine. The coming 12 to 18 months mark the most data-rich window of observation humanity has ever had for an interstellar visitor. A fleet of ground-based and space-based observatories will track 3I Atlas through its entire passage around the Sun, documenting in real time how its activity, morphology, and chemistry shift in response to changing solar illumination. This campaign promises not only an unprecedented sequence of images and spectra, but also a living demonstration of how the scientific method confronts enigmas. Communicating such an evolving story to the public requires careful balance. The rhythms of scientific inquiry, hypothesis, testing, refinement unfold on timescales that rarely align with media cycles or public hunger for definitive answers. Peer review, replication, and independent analysis stand as guardrails, ensuring that startling results are interrogated before they calcify into conclusions. The early mass estimates for Atlas, suggesting a nucleus of tens of billions of tons, will inevitably undergo rigorous scrutiny as methods and assumptions are dissected by the community. Historical precedent tempers excitement with perspective. Astronomy's archives are filled with anomalies that at first seemed revolutionary, only to yield conventional explanations once data improved and theoretical models matured. This is not failure, but self-correction, the essence of science refining itself through iteration. The very timing of Atlas's discovery may reflect nothing more exotic than our own technological progression. Earlier generations of surveys lacked the sky coverage, cadence, and follow-up infrastructure needed to identify and characterize such bodies. Only now, with global telescope networks, rapid response pipelines, and space telescopes on standby, are we prepared to detect and study them in detail. For educators and the public, Atlas is an opportunity to witness science unfolding as a process rather than as a list of final answers. It provides a vivid case study in hypothesis testing, statistical reasoning, and recognition of observational bias, demonstrating how evidence accumulates slowly until clarity emerges. From a cosmic perspective, every interstellar object carries the memory of environments we cannot visit, relics of processes operating over billions of years across stellar systems scattered through the galaxy. Whether Atlas proves typical or rare, it is a messenger from that wider ecosystem. The true resolution of current debates about mass, chemistry, and demographics will come not from a single case, but from the statistics of many. Within this decade, the Vera Rubin Observatory and other surveys will shift the field from anecdote to population science, revealing whether Atlas was an outlier or the herald of a larger pattern. Either way, it defines an observational watershed. Its study is shaping techniques, protocols, and expectations that will guide how we approach the next wave of interstellar wanderers. And soon, the most tantalizing perspective awaits. A view of Atlas as it sweeps past Mars, offering an entirely new vantage on a body already rewriting the boundaries of interstellar astronomy. Part 10. The Mars Encounter. The cosmic choreography that carries 3I Atlas to within 30 million kilometers of Mars on the 3rd of October in the year 2025 creates an observational opportunity without precedent. This encounter distance of roughly 0.2 astronomical units places the interstellar visitor well within reach of Mars-based spacecraft, offering the tantalizing prospect of humanity's first close-up perspectives on an object born beyond the solar frontier, viewed not from Earth but from assets already orbiting another planet. The European Space Agency maintains 2 long-serving emissaries around Mars that could, with careful planning, contribute to this campaign. Mars Express, launched in 2003 and still functioning more than 2 decades later, carries imaging instruments capable of sensitive photometric observations. The Trace Gas Orbiter, which arrived in 2016 under the ExoMars program, possesses spectroscopic capabilities that might be adapted to monitor Atlas during the passage, though power budgets and pointing constraints will require intricate mission planning. NASA fields several additional candidates. MAVEN, in orbit since 2014, was designed to probe atmospheric escape, but includes instruments that could conceivably track the interstellar comet if managers adjust pointing sequences. The Mars Reconnaissance Orbiter, operational since 2006, houses the famed HiRISE camera, though the enormous encounter distance renders detailed imagery unlikely. HiRISE specializes in resolving meter-scale features on the Martian surface, not kilometer-scale objects tens of millions of kilometers away. Still, even basic photometry and brightness profile data from Mars orbit would provide unique vantage points unattainable from Earth. The scientific value lies in geometry. From Mars, Atlas will be seen against different backgrounds, at distinct phase angles, and under scattering conditions that diverge from terrestrial perspectives. Such vantage points could reveal coma asymmetries, dust scattering behavior, and gas distribution patterns otherwise hidden. Photometric measurements from multiple angles offer constraints on activity levels and help evaluate the controversial mass estimates that depend on linking visible outgassing to orbital recoil. Coordinating these efforts across planets represents a logistical feat. Light requires approximately 16 minutes to travel between Earth and Mars during the encounter, precluding real-time commands, but allowing planned sequences. Communication windows during early October remain favorable for downlinking data. Mission managers will need to choreograph observation schedules carefully, balancing Atlas with primary mission goals, while ensuring data flow integrates smoothly into the global campaign. The observational window spans several days around the close approach. As Atlas moves relative to Mars's sky, each orbiter's position and orbital period will determine specific opportunities. Predictions suggest brightness levels well within the sensitivity of instruments aboard the more capable Mars orbiters, though detectability depends on coma development, dust production, and the inherent brightness of the nucleus. Models based on Earth-based monitoring provide estimates, but the object's behavior remains unpredictable as it absorbs increasing solar heat. From Earth, the geometry is far less forgiving. As Atlas approaches perihelion, its apparent position sinks toward the glare of the Sun, making telescopic study increasingly difficult. Mars orbiters escape this handicap, peering from a different perspective and free from atmospheric interference. Safety concerns are negligible. 30 million kilometers equals roughly 5 times the distance between Earth and the Moon, close in cosmic terms, but utterly safe for Martian spacecraft. The risk is essentially zero, while the potential scientific return is considerable. Precedent exists for Mars-based observations of asteroids and comets, though none have involved an interstellar object of such intrigue. Technical hurdles remain formidable. Instruments must be repurposed from their usual tasks of imaging Martian terrain or probing the atmosphere. Pointing accuracy must be precise to lock onto a faint-moving target across interplanetary distances. Calibration pipelines designed for surface science must be adapted for distant photometric sources. Yet history shows that mission teams excel at creative repurposing when opportunities of this rarity arise. Integration of data from Mars orbiters with Earth-based facilities will demand meticulous cross-calibration. Differences in detector sensitivity, filter systems, and vantage geometry must be reconciled through modeling so that combined analyses produce meaningful results. Expectations must remain measured. These observations will not reveal the fine structure of the nucleus, but could deliver brightness curves, phase angle responses, and low-resolution coma morphology. Even modest returns will enrich the record, offering angles of insight inaccessible from Earth during this critical phase. The broader narrative elevates this moment beyond mere technical exercise. For the first time, humanity may observe an interstellar visitor, not from its home planet, but from a second world, extending our cosmic gaze outward through instruments circling Mars. Atlas thus becomes not just an object of scientific curiosity, but a symbol of our expanding observational footprint, bridging planets to study the messengers that drift between stars. The Mars Encounter Observation Campaign offers a glimpse of the future, when multiple spacecraft scattered across the solar system routinely combine perspectives to study transient phenomena. As interplanetary missions multiply and capabilities advance, such coordinated campaigns will become the norm for asteroids, comets, and other cosmic visitors. Communicating these efforts to the public requires balancing sober realism with genuine excitement. The distances involved rule out the dramatic high-resolution images that usually capture imagination, yet the scientific value of multi-vantage photometry and astrometry is immense, revealing details about activity levels and orbital dynamics that no single viewpoint could capture. The October observations from Mars's orbital perspective are best understood as a prelude, the opening act of a longer campaign that will follow Atlas through the inner solar system. For mission planners, opportunity must be weighed against practical constraints: spacecraft health, power budgets, communication windows, and the unyielding priorities of primary science goals. Both the European and American space agencies will decide participation based on feasibility and available resources, but even partial involvement underscores the growing ability to mobilize a planetary network of observers. Regardless of which spacecraft ultimately contribute, the encounter represents a historic first. Multiple assets positioned on different worlds, simultaneously watching a visitor from interstellar space. Such alignments are rare, and they provide irreplaceable insight into dust scattering, gas production, and the evolution of cometary comae under solar heating. The datasets returned from Mars orbit, when integrated with continuous Earth-based monitoring, will offer a record of 3I Atlas unmatched by any previous interstellar object. And this campaign is not an endpoint but a bridge, leading toward an even more spectacular opportunity as the visitor races onward toward its looming gravitational encounter with Jupiter. Part 11. The Jupiter Opportunity. The gravitational choreography that will carry 3I Atlas to within just over 53 million kilometers of Jupiter on the 16th of March, in the year 2026, represents the most scientifically valuable moment of its entire passage through the solar system. At slightly more than 1/3 of an astronomical unit from the gas giant, the interstellar visitor enters the realm where in situ spacecraft observations become conceivable. NASA's Juno spacecraft, launched in 2011 and still conducting extended operations around Jupiter, stands at the center of these possibilities. Although Juno was not designed for deep space interceptions, researchers including Avi Loeb, Hibbard, Crowell and their collaborators have outlined daring proposals to redirect the probe toward an intercept trajectory with 3I Atlas. The engineering would be formidable, yet the science at stake is nothing less than humanity's first close-up encounter with an object born beyond the stars. The mechanics involve exploiting what aerospace engineers call the Oberth effect. By executing engine burns when Juno sweeps through its closest approaches to Jupiter, where velocities climb to extraordinary values, each unit of propellant yields maximum momentum change. In essence, Jupiter's enormous gravity becomes part of the spacecraft's engine, amplifying the effectiveness of every drop of fuel. The calculations are intricate, demanding exquisite precision in timing, burn duration, and alignment with both Juno's elliptical orbit and the predicted trajectory of 3I Atlas. But the rewards are equally staggering. Direct sampling of dust, isotopes, and plasma in the object's coma would move the debate from inference to evidence, providing hard measurements of grain composition, thermal behavior, and volatile release mechanisms. The nickel without iron puzzle that has so intrigued astronomers could be tested directly, either confirmed as a natural chemical peculiarity or dismissed as an artifact of remote spectroscopy. Carbon dioxide-rich ices, isotopic ratios, and refractory element abundances could be measured rather than speculated upon. No telescope, no matter how large, can provide this level of detail. The excitement has already spilled beyond scientific circles. Members of the United States Congress formally requested that NASA examine the feasibility of repurposing Juno for this purpose, reflecting the powerful cultural resonance of studying a messenger from interstellar space. yet risk-benefit analysis tempers enthusiasm with hard reality. Juno's current mission objectives focus on mapping Jupiter's gravity field, magnetic environment, and atmospheric structure. Diverting to chase 3I Atlas would end those programs permanently. The spacecraft carries limited propellant reserves, sufficient for orbital adjustments and station keeping, but not for major course changes. An intercept would require burning essentially all remaining fuel, sacrificing further Jovian science in pursuit of interstellar payoff. Engineers must weigh feasibility with ruthless honesty. Can Juno's propulsion system deliver the velocity change required? Can the timing of its perijove burns align with Atlas's passage? The uncertainties are immense. Even if theoretically possible, margins would be razor-thin, and any miscalculation could strand the spacecraft on a trajectory that achieves neither Jovian science nor interstellar encounter. Still, the prospect of transforming a mature planetary orbiter into a pioneering interstellar probe is difficult to ignore. Alternative strategies exist. The European Space Agency's JUICE mission, now en route to the Jovian system, may achieve favorable alignments for distant observations, though its arrival timing reduces the likelihood of a close intercept. NASA's Psyche spacecraft, heading for the metallic asteroid that bears its name, might contribute depending on trajectory geometry. Meanwhile, Earth-based observatories will continue monitoring relentlessly. Hubble, the James Webb Space Telescope, and the new generation of extremely large ground-based telescopes will all participate. The forthcoming Spherix, all-sky surveyor, could add crucial infrared data, mapping Atlas's extended carbon dioxide coma with a wide field unmatched by other assets. The policy implications extend far beyond Atlas itself. If humanity faces similar opportunities in the future, or even potential threats, decision frameworks must already exist. The debates surrounding Juno's possible redirection highlight the need for interstellar visitor protocols rules for weighing costs against unprecedented scientific gain. Should planetary defense and planetary science missions be designed with latent flexibility for opportunistic encounters? Should international consortia pool resources to ensure rapid response capabilities? 3I Atlas is forcing those questions into the open. At its heart, the debate reflects the tension between known science and unknown promise. Continuing Juno's Jovian mapping guarantees further insights into planetary magnetospheres and atmospheric dynamics. Redirecting Juno risks all of that for the possibility, though not the certainty, of answering some of the deepest questions about interstellar matter. Is Atlas natural or technological? Is it typical or anomalous? Do its chemical fingerprints reveal alien stellar nurseries or exotic physics? Only direct contact can resolve these mysteries. Whatever decision emerges, March of 2026 will mark a defining moment. Either Juno makes its fateful pivot toward the interstellar path, or Earthbound instruments watch from afar while the visitor sweeps past Jupiter's domain and continues toward the inner solar system. In both cases, the gravitational embrace of Jupiter provides the stage for science at its boldest. A choice between continuing a journey already underway or leaping into the unknown, pursuing a messenger from beyond the stars while the opportunity exists, knowing such chances may not come again for generations. The observation geometry during the Jupiter encounter offers both remarkable advantages and unavoidable disadvantages. At the distance of the outer solar system, telescopes and spacecraft operate free from the overwhelming glare of the Sunday. This clear vantage point allows clean measurements of coma structure, tail dynamics, and faint emissions that would be far more difficult to extract near perihelion. Yet the same geometry that provides clarity also introduces challenges. The vast gulf separating Jupiter from Earth weakens the object's apparent brightness for ground-based telescopes, demanding longer integrations and more sensitive instruments to achieve usable data. Communication delays, already nearly an hour for two-way signals, complicate real-time operations and require carefully pre-programmed command sequences. Mission timeline constraints add urgency to every discussion. Orbital redirection cannot be improvised at the last moment. Months of modeling, planning, and testing must precede any attempt to adjust Juno's trajectory. If NASA chooses to pursue an intercept, approval must come early enough to permit navigation teams to calculate precise burns, confirm propellant margins, and update spacecraft systems for the radically different mission profile. The encounter also presents a natural opportunity for international cooperation. European and Japanese space agencies both operate missions in the Jovian system, and coordinated observing campaigns would multiply the scientific return. Sharing of data, joint analysis of spectral signatures, and the pooling of expertise across continents would not only maximize knowledge, but also demonstrate the collaborative spirit that defines modern planetary science. The global fascination with 3I Atlas makes such partnerships as politically attractive as they are scientifically valuable. Public engagement forms another dimension of the encounter. The decision whether or not to repurpose Juno offers an educational case study in aerospace governance, explaining how space agencies weigh competing priorities, balance scientific promise against engineering risk, and allocate finite resources under uncertainty provides a window into how exploration decisions are made. Historical precedents such as the Deep Impact spacecraft's redirection toward Comet Hartley 2 or repurposed asteroid encounters by probes initially bound for other targets show that flexibility in mission planning can deliver extraordinary rewards. The technical requirements for Juno are formidable. Precise navigation solutions, recalibrated instruments for dust and volatile studies, thermal management during extended cruise phases, and modified communication protocols for long-range operations all stand as non-trivial challenges. Juno's payload, however, remains scientifically powerful. Magnetometers, microwave radiometers, infrared imagers, and charged particle detectors could probe 3I Atlas in ways impossible from Earth. Any encounter would almost certainly be the spacecraft's final act, a last great gesture before its systems fail. Whatever the final decision, the Jupiter passage has already highlighted the extraordinary scientific magnetism of 3I Atlas. Whether through daring spacecraft interception or through coordinated Earth-based and space-based campaigns, the data collected during this phase will test every theoretical framework proposed to explain the object's baffling nature. For theorists and observers alike, the coming year represents a turning point in interstellar object astronomy, when speculation yields to evidence and the cosmos forces its secrets into view. Part 12. The Theoretical Fallout. The theoretical implications of 3I Atlas extend far beyond the characterization of a single mysterious object. Its presence forces astronomy to grapple with fundamental questions about how planetary systems form, how debris migrates between stars, and how the chemistry of matter evolves over the lifetime of the galaxy. Whether the preliminary mass estimates ultimately prove accurate or are significantly revised, the object has already carved its place in scientific history as a driver of new theories. If subsequent analysis confirms a nucleus spanning roughly 5 kilometers in diameter, with a mass on the order of 33 billion tons, population models of interstellar debris face profound challenges. Current ejection mechanisms, from planet to planet scattering to gravitational slingshots during stellar flybys, struggle to explain how such massive bodies can be launched intact from their birth systems. To eject kilometer-scale nuclei without breaking them apart through tidal stresses or collision cascades, requires either rare alignments of geometry or physics not yet fully appreciated. Stellar flyby scenarios may need wholesale re-evaluation, and scattering models will require deeper exploration of rare but possible configurations capable of hurling giants into the void. Alternatively, if the mass estimates are eventually reduced, the lesson would still be invaluable. Such an outcome would demonstrate how cometary coma and outgassing processes can mislead observers into inferring inflated properties. That would not be failure, but progress and advance in understanding how non-gravitational forces, sublimation dynamics, and momentum transfer between gas jets and nuclei complicate the apparently straightforward relationship between activity levels and acceleration limits. 3I Atlas, in that case, would become the benchmark for refining models of comet physics, forcing recalibration of assumptions applied to both interstellar and homegrown examples. The chemical anomalies guarantee theoretical consequences regardless of final mass estimates. The detection of nickel emission lines in the absence of iron features overturns expectations drawn from decades of cometary spectroscopy. Iron and nickel generally emerge together, born from the same nucleosynthetic processes, and usually released in tandem when metal-bearing minerals sublimate or fracture. To find nickel blazing while iron remains invisible demands creative chemistry, perhaps photon, stimulated desorption liberating nickel atoms more readily than iron, or the breakdown of organometallic compounds with selective release patterns. Thermolysis of exotic carbonyl complexes remains another possibility. Testing these scenarios will require not only telescope time but also laboratory experiments, recreating low-temperature, low-pressure conditions where such unusual pathways might operate. The carbon dioxide-rich signature observed by the James Webb Space Telescope adds yet another dimension to the puzzle. Such compositions point to birthplaces far beyond the carbon dioxide snowline of a parent system, where ambient temperatures fall below -125 degrees Celsius. To model the chemistry of these environments is to explore regions where solar system analogues rarely exist. If 3I Atlas formed in such extreme peripheries, its very survival as a solid body over billions of years of interstellar exposure speaks to robust structures and resilient ices, unlike those found in typical comets closer to home. Morphological modeling must now address why the object produced a persistent sunward glow and an evolving antitail that defied conventional expectations. These features, captured repeatedly by the Hubble Space Telescope and ground-based observatories, suggest unusual grain dynamics and forward scattering geometries. Theoretical work here will ripple outward, informing not only interstellar studies but also the physics of solar system comets that display similar though less pronounced behaviors. Explaining why Borisov, our second interstellar visitor, behaves so normally while 3I Atlas insists on breaking rules may reveal deep truths about the diversity of stellar environments that seed these wanderers. Population statistics remain the most consequential frontier. If giants like 3I Atlas prove common, theories of planetary system evolution must reckon with ejection processes capable of populating the interstellar medium with kilometer-scale bodies. The Vera Rubin Observatory's legacy survey of space and time will soon provide the sample sizes necessary for rigorous tests. Within a few years, the debate will shift from speculation based on 3 objects to data-driven analysis grounded in dozens or hundreds of detections. Predictions about size distributions, chemistry, and orbital alignments can then stand or fall against a statistically robust dataset. The planet seeding hypothesis also gains traction from such observations. If massive interstellar visitors are indeed frequent, then their role as ready-made seeds captured by young stellar disks must be taken seriously. Theoretical work will need to refine capture cross-sections, evaluate survival probabilities under violent disk conditions, and model the growth trajectories of captured seeds into gas giants or super-Earths. In that framework, 3I Atlas represents not only an enigma, but also a potential exemplar of the very building blocks that shape planetary systems across the Milky Way. One way or another, the object has already achieved what few discoveries manage. It has forced scientists to reconsider first principles, opened new avenues of investigation, and reminded us that the universe still has the power to surprise even the most careful models. The seeding scenarios demand coupling stellar dynamics, disk evolution, and planetary formation physics in ways that stretch even the most advanced computational frameworks. If interstellar visitors like 3I Atlas are captured regularly by young stellar systems, the process could represent a previously unrecognized pathway for accelerating the birth of giant planets. The implications ripple far beyond technical astronomy into the cultural sphere, raising questions about how scientific communities respond to anomalous data and where the line should be drawn between bold speculation and unfounded conjecture. 3I Atlas has become a case study in this tension. Its unusual properties, mass estimates stretching into tens of billions of tons, chemical signatures rich in carbon dioxide but poor in iron, and morphological oddities like the persistent sunward glow have inspired vigorous theoretical debate. Yet in parallel, the object has become a magnet for media amplification, where speculative ideas too easily transform into definitive claims through repetition across headlines and social networks. The experience illustrates both the benefits and hazards of conducting frontier science in the social media age, where genuine excitement about discovery can become entangled with misinterpretation and premature storytelling. For theorists, the challenge now lies not only in accuracy, but also in anticipation of miscommunication. Future science communication strategies will need to balance legitimate enthusiasm with caution, emphasizing which findings remain provisional and which have passed through the crucible of peer review. Historical precedent suggests that the path forward will involve years, perhaps decades, of refinement. Anomalous observations often provoke a proliferation of competing explanations before consensus slowly emerges. In this sense, 3I Atlas joins a long lineage of astronomical puzzles that forced theory to evolve through repeated confrontation with stubborn data. No single explanatory framework currently accounts for the full range of observed anomalies. Interdisciplinary collaboration has therefore become essential. Astronomy, planetary science, chemistry, and physics must combine perspectives to build composite models that can address metal emissions, dust dynamics, and unusual volatile ratios in a unified manner. Laboratory experiments will prove central to this effort. By simulating the low-temperature, low-pressure environments characteristic of cometary comae, researchers can test whether photon-stimulated desorption or the thermolysis of organometallic compounds truly releases nickel without iron, and whether exotic ice mixtures could reproduce the observed carbon dioxide dominance. On the computational side, models must advance dramatically to incorporate the multi-physics reality of such objects. Gas dynamics, dust transport, chemical reaction networks, and radiative transfer all intersect in ways that tax current numerical codes. 3I Atlas becomes a proving ground not just for cometary theory, but for the computational techniques that will underpin planetary formation studies across the galaxy. Even if its mysteries eventually yield conventional answers, the theoretical progress inspired by the object will resonate across multiple fields, from interstellar medium research to the study of protoplanetary disks. The true scientific value of 3I Atlas may lie less in what it is than in what it provokes. Its anomalies have already forced astronomers to generate testable hypotheses, predictions that forthcoming observations will either confirm or reject. In this sense, it acts as a catalyst for falsifiable science, an engine for deeper understanding of how matter behaves and evolves in the cosmic arena. Whether remembered as revolutionary or conventional, 3i Atlas has succeeded in pushing theory to think more broadly about the spaces between stars. It is against this backdrop of genuine scientific ferment that the more speculative, even fringe interpretations of its nature must now be weighed. Part 13. The Fringe and the Faithful. The media ecosystem swirling around 3i Atlas reveals the complicated choreography of how scientific uncertainty transforms into public narrative. In one corner, some outlets amplify technological interpretations, hinting at artificial origins. In another, skeptics push back with equal force, reminding audiences that comets often surprise us but remain natural phenomena. This polarization underscores the challenges of communicating genuinely anomalous observations in an era where nuance is too often stripped away in the rush toward definitive explanations. Surveying coverage across different platforms shows just how dramatically the same data can be reframed. One article emphasizes the improbability of the orbital geometry and the strangeness of the mass estimates, building toward an air of mystery. Another stresses the preliminary nature of those numbers, reminding readers that natural comet physics can account for most observed behavior if one adjusts assumptions. The technological narrative finds its most visible champion in Harvard astronomer Avi Loeb, yet his statements, when examined closely, are more measured than the headlines suggest. Loeb frames artificial origins not as conclusions, but as hypotheses worth investigating when conventional physics appears inadequate. His method involves calculating probabilities for various scenarios and comparing the likelihood of natural explanations against artificial ones. This is hypothesis generation in the classical scientific sense, though in translation to the public stage the boundary between speculation and conclusion often becomes blurred. Critics argue that extraordinary claims demand extraordinary evidence, and the case of 3i Atlas simply does not meet that threshold. Yes, the mass estimates suggest tens of billions of tons, and yes, the non-gravitational acceleration appears unusually small for such an active comet, but neither anomaly proves artificial design. Natural explanations remain on the table: exotic ice chemistries, unusual dust-to-gas ratios, or forward, scattering effects that trick our eyes into seeing a sunward glow. The orbital geometry debate illustrates how statistics can be read in different lights. A mere 4.1 degree inclination relative to the ecliptic plane occurs randomly in perhaps one case out of 500, and advocates of the artificial hypothesis present this as improbably convenient alignment. Critics respond that survey selection effects bias us toward finding ecliptic-aligned objects in the first place. What seems improbable may simply reflect how our telescopes are pointed. The perihelion timing creates similar interpretive divergence. The comet's closest approach to the Sun happens on the far side, from Earth's perspective, generating several months of blackout when solar glare blinds our telescopes. Some articles spin this as intentional evasion, as though the object chose to hide. Others patiently explain orbital mechanics. 3. I-Atlas follows a hyperbolic trajectory set by its velocity vector and the Sun's gravity, not conscious decisions. NASA's official statements take this second view. The agency adopts standard scientific conservatism, assuming natural explanations until data compels otherwise. Its communications explicitly address evasion narratives by explaining that perihelion placement results from geometry alone. The mathematics leaves no room for intention. Quality science coverage often outlines what would constitute true smoking guns for artificial origin. Sustained maneuvers beyond outgassing physics, coherent narrowband radio transmissions, engineered reflectance patterns, or abrupt non-ballistic trajectory changes, these would force reconsideration. In their absence, the prudent conclusion is that current data remain insufficient to support extraordinary claims. Meanwhile, skeptics remind audiences that visible tails, volatile spectra, and evolving comae are exactly what astronomers expect from active comets, whether born in our solar system or beyond. 2I Borisov, discovered in 2019, behaved precisely like local comets, serving as the benchmark of normality against which 3I Atlas's quirks can be compared. Yet the communication battle is not simply about facts, but about how those facts travel. Modern science flows through multiple channels, each with its own standards of credibility. Peer-reviewed journals stand at the top of the hierarchy, but conference presentations, preprint servers, blogs, press releases, and social media all play roles in shaping perception. Preprints in particular accelerate this process. The mass estimates for 3I Atlas circulated first as preprints before formal publication, ensuring rapid discussion but also exposing preliminary findings to public interpretation before reviewers could weigh in. Blogs and personal essays offered further speculation, blending technical detail with imaginative extrapolation. While these formats encourage creativity and transparency, they also allow speculation to gain a veneer of authority through viral repetition rather than rigorous evaluation. Press offices play their own role, translating technical findings into stories intended for wide audiences. Some of the coverage around 3I Atlas demonstrates how well this can work when caveats are preserved and context provided. Other pieces illustrate the dangers, where a carefully hedged possibly becomes a definitive probably by the time it reaches a headline. Social media then acts as an amplifier, recycling fragments of speculation until they echo as if they were consensus. The feedback loop creates the impression of growing certainty, even as the underlying data remain unchanged. Quality science journalism provides the antidote. The best reporting distinguishes between what scientists have actually said and what others interpret from it. It acknowledges uncertainty, presents competing hypotheses, and reminds readers of the ordinary scientific process. When done well, such journalism not only communicates discoveries, but educates audiences about how science itself works, how anomalies trigger new ideas, how hypotheses are tested, and how consensus gradually forms. Educational opportunities abound in the case of 3I Atlas. Students and the public can watch in real time as the scientific method plays out on a frontier discovery. They see hypothesis generation, probabilistic reasoning, critical evaluation, and debate among experts. They also witness how cultural context, our long fascination with extraterrestrial intelligence, our appetite for extraordinary stories, can shape interpretation. In this sense, the debate surrounding 3I Atlas teaches as much about the sociology of science as about astronomy itself. The comet therefore stands not only as a physical object hurtling through space, but as a mirror reflecting how 21st century society processes the unknown. It shows how evidence, probability, speculation, and narrative intertwine, and how fragile the boundary can be between wonder and overstatement. 3I Atlas provides a rare real-time case study in how science actually works. Here, before our eyes, the object illustrates the full cycle of hypothesis generation, peer review evaluation, and the gradual accumulation of evidence that either strengthens or dismantles initial proposals. It shows how genuine astronomical mysteries can simultaneously attract legitimate research and fringe speculation, often blurring in public perception. To distinguish rigorous investigation from unfounded conjecture requires understanding the standards by which professional astronomy measures evidence. Media literacy becomes critical in this environment. In today's information landscape, legitimate uncertainty is frequently confused with definitive knowledge. Preliminary findings are too easily presented as settled fact, and extraordinary claims compete for attention against more mundane but scientifically stronger explanations. Viewers and readers need tools to evaluate scientific claims critically, while still holding on to the excitement of discovery. A culture of scientific thinking must balance open-mindedness with disciplined skepticism, not lapsing into uncritical acceptance, but not dismissing every unusual observation as fantasy either. Even the fringe discussions around 3i Atlas serve valuable functions. They reveal deep public engagement with questions at the edge of science. They motivate researchers to refine conventional models with greater rigor, and they open educational opportunities to show how scientific communities grapple with puzzling data. Such debates, though messy, illuminate science as a living process rather than a collection of final answers. Future communication about anomalous discoveries will benefit from the lessons learned during this media cycle. Clear labeling of preliminary results, explicit presentation of multiple explanatory frameworks, and honest articulation of uncertainty can preserve public enthusiasm without distorting what scientists actually know. The faithful adherence of various interpretations, whether natural, artificial, or exotic, ultimately contributes to progress when channeled through methodology. Intellectual diversity, tempered by rigorous testing, keeps the field from premature consensus built on insufficient evidence. This diversity is not a weakness but a strength, driving the creative thought necessary to confront phenomena that resist easy explanation. Epilogue: The Silent Giant's Legacy. As 3i Atlas continues outward, slipping once again toward the darkness of interstellar space, it leaves behind more questions than answers. Yet in doing so, it has already changed astronomy. This silent giant has compelled scientists to recognize that the universe still operates on scales and through processes that challenge even our most sophisticated theories. Whether the nucleus truly spans 5 kilometers and weighs more than 33 billion tons, or whether those estimates are revised downward, whether its strange chemistry proves conventional or revolutionary, the object has accomplished something remarkable. It has transformed the study of interstellar visitors from curiosity into systematic science. The methods forged in response to Atlas precision astrometry campaigns involving hundreds of observatories, rapid response protocols, linking ground and space-based telescopes, chemical modeling of volatile ices and exotic compounds will serve for decades to come. Every future interstellar object will be tracked, analyzed, and understood using infrastructure built in the crucible of this discovery. The silent visitor has become the template for how astronomy organizes itself in an era of rapid detection and global collaboration. More profoundly, 3i Atlas has reminded us that the gulf between stars is not empty. It is a reservoir of ancient debris, a river of cosmic material flowing between systems, carrying the fingerprints of planetary births and stellar deaths across galactic time. Each interstellar visitor is a messenger, bearing within its chemistry and structure the history of environments we can never visit directly. The planet seeding hypothesis, the technological speculation, the statistical puzzles, and the chemical anomalies of Atlas will continue to drive inquiry long after the comet itself vanishes from telescopic view. The questions it raised about how such objects are launched, how they survive their journeys, and how we detect them strike at the heart of cosmic evolution. In a broader sense, Atlas embodies the uncertainty that makes science compelling. We live in an age when instruments are powerful enough to surprise us, when preliminary data can shake long-standing frameworks, and when the next discovery could overturn assumptions about our cosmic neighborhood. That capacity for surprise, for real discovery, is one of humanity's most precious intellectual assets. The media storm, the public engagement, and the educational dialogue surrounding Atlas reveal something reassuring. Curiosity about the universe is alive and well, even in an era often characterized by polarization and cynicism. People still want to know whether we are alone, how planets form, and what secrets drift in the space between stars. These are human questions that cut across culture, politics, and ideology. As the next generation of surveys, led by the Vera Rubin Observatory, begins to flood us with new interstellar detections, Atlas will stand as both outlier and catalyst. Large populations will allow statisticians to move from speculation to measurement, from anecdotes to patterns. Yet the uniqueness of this giant should not be forgotten. Population studies will reveal trends, but individual visitors like Atlas, with their singular quirks, will continue to capture imagination. The legacy extends beyond data. It shapes how we evaluate evidence, how we test competing hypotheses, and how we build consensus. It teaches that speculation has its place, but only when tethered to testable predictions. It reminds us that skepticism is not dismissal, but discipline. In the end, whether Atlas is remembered as a massive natural comet carrying exotic chemistry from an alien system, a statistical outlier appearing at the dawn of our interstellar survey era, or something still more extraordinary, it has already earned a place in astronomical history. It forced us to sharpen our methods, broaden our imagination, and look more carefully at our assumptions. The silent giant will vanish into the dark, but the questions it raised and the tools it inspired will endure. Atlas thus represents both conclusion and prologue, the end of humanity's first tentative reconnaissance of interstellar visitors, and the beginning of a new era where the galaxy itself becomes our laboratory. The next traveler may be smaller or stranger, more ordinary or more alien. Whatever it is, we are better prepared because of Atlas, and that may be its greatest legacy, teaching us not just about itself, but about how to face the mysteries that still lie waiting in the cosmic deep.